I'm the professor of Mechanical Engineering Department. The course name is Unconventional Machining Process. Already we have discussed that. The topic is Electron Beam Machining Process Parameters and Capabilities and Advantages and Disadvantages of Electron Beam Machining. Okay, right. These two are the course learning outcomes of the today's topic. Okay, at the end of this session, students will be able to understand the electron beam machining process parameters and capabilities. The second course learning outcome is that explain the EBM advantages and disadvantages. However, in this topic, I will give you a brief on the non-traditional machining process, and subsequently we are dealing or discussing the electron beam machining process parameters and its working, and subsequently we are going to discuss the today's topics: process parameters and capabilities and advantages and disadvantages of electron beam machining. Right. Non-traditional machining process. Under this, there are three main categories: mechanical, thermal, chemical and electrochemical. Under mechanical, USM ultrasonic machining, WJM water jet machining, AWJM abrasive water jet machining, IJM ice jet machining. Okay, so far we have discussed these three. Okay, if time permits, we will discuss this one later. Right. Under chemical and electrochemical, chemical milling, plasma chemical milling, electrochemical milling. Under thermal category, electro discharge machining, electron beam machining, laser beam machining, ion beam machining, plasma beam machining. Okay. In today's topic, we are focusing on electron beam machining. So in this, we are going to discuss the process parameters and capabilities, advantages and disadvantages of electron beam machining. So before we learn these things, we will discuss a brief on working of each element or segment of the electron beam machining and few of the applications. Okay, right. Now let us see the parameters affecting electron beam machining performance. Okay, so in the last presentation we have discussed the same thing here: electron beam machining and its influence on removal rate, surface quality and accuracy because of these process parameters. Okay, the main process parameter is working material, emission current, power density, EBM pulse, time. Right. Now, in working material, thermal properties, thickness, ceramic, superalloy. These are the various working materials associated to this electron beam machining. Emission current, voltage, cathode. In power density, current, voltage, beam cross section. Okay. In EBM pulse duration, energy, frequency, acceleration, voltage. Regarding time, removal and pulse. Second one is frequency. So these are the various parameters affecting the performance of electron beam machine. Right, now let us see the basic equipment of electron beam machining. Okay, so here the main components of EBM with vacuum chamber with 1 into 10 power minus 4 torque. Okay, so electron gun, which consists some other extended elements, cathode, electron emitting filament, grid cup, anode positive, electron stream, magnetic lens, local heating, fusing and vaporizing on the surface of the workpiece material. That is the main requirement and purpose of this electron beam machine. Okay. So here high vacuum pump is created to create vacuum in the shield. Okay, and this is beam port. This is the workpiece fixed on the or mounted on the table. Okay, right. We'll see the filament material. Tungsten filament cathode is heated to about 2500 to 3000 degrees centigrade in order to emit electrons. Okay, so it emits the electrons at the temperature 2500 to 3000 degrees centigrade. Okay, the measure of this effect is the emission current, the magnitude of which varies between 20 and 100 milliamperes. Right, right. Parts of electron beam machine. Now let us discuss the individual main parts of this electron beam machine. Okay, so here vacuum chamber is the main important element. Okay, right. The electron gun plays a pivotal role in electron beam machining and comprises one of the essential components. So however, this entire setup is with vacuum chamber that we will discuss later. Okay, now let us discuss this electron gun. Okay, the electron gun plays a pivotal role in electron beam machining and comprises one of three essential components. Okay, the first one is the tungsten filament. Okay, connected to the negative terminal of the DC power supply, serves as the cathode and emits electrons. So this one. Okay, so electron gun here plays an important role. Okay, so the tungsten filament connected to negative terminal of the DC power supply serves as the cathode and emits electrons. Okay, so this is tungsten filament. Okay, right. First one over. Okay, now second one, the grid cup. Okay, second one, the grid cup. The grid cup negatively biased relative to the filament helps guide the emitted electrons. So this grid cup acts as the guiding element. Okay, right. The grid cup negatively biased relative to the tungsten filament helps guides the emitted electrons. Okay, this helps guide the emitted electrons. This cathode or electron emitting tungsten filament emits the electrons, but here grid gap guides the emitted electrons. Okay, now the third one, anode. Okay, anode. The anode connected to the positive terminal of the DC power supply plays a crucial role in the acceleration of electrons. Okay, so here positive terminal and negative terminal. Okay, the cathode. Okay, so here positive terminal is connected to the anode. Okay, the anode connected to the positive terminal of the DC power supply. Okay, the grid cup negatively biased relative to the filament. Okay, helps guide the emitted electrons. Okay, so here anode accelerates the electrons. Okay, here the grid cup guide the emitted electrons. Okay, just guides. Okay, so here the anode plays a predominant role in the acceleration of electrons. Okay, right. Together, these components ensure the generation and control of the electron beam. Okay, so here generation means the grid gap will guide the emitted electrons. Okay, where it will generate? The tungsten filament. Okay, so here emits electrons means generate. Okay, so here the tungsten filament emits the electrons or generate the electrons. Okay, and grid cup directs or guide the emitted electrons. Okay, the anode accelerate the electrons. Okay, that is nothing but control of the electron beam. Okay, right. So here three important components have been over. Now vacuum chamber. This is what I told in the beginning, but in terms of the importance, the electron gun would be the first point. But however, the entire setup will be with vacuum chamber casing. Okay, right, vacuum chamber. Right, here obviously the electrons will collide with each other usually. Okay, right, but here to prevent collisions of accelerated electrons with air molecules, the EBM setup is enclosed with a vacuum chamber, maintaining a vacuum level typically ranging from 10 power minus to 10 power minus 5 mm of mercury. That is nothing but 10 power minus 4 torr. Okay, so see, these electrons may travel in random direction or maybe in unspecified direction. Okay, so because of the influence of the air, these electrons may collide each other. Okay, these electrons may collide each other, but we have set up a vacuum chamber with a vacuum ranging from 10 power minus 4 to 10 power minus 5 mm of mercury to prevent the collision of accelerated electrons. Okay, understanding? Right. That is about vacuum chamber and its importance. Okay, in the EBM setup, we have created vacuum with 10 power minus 4 to 10 power minus 5 mm of mercury to prevent the collisions of electrons with the uh, setup. Okay, right. Right. This chamber includes a door through which the workpiece is positioned on the work table before being sealed. Okay, see here, the workpiece is set up on the table and the chamber includes a door. Here some viewing port is there, so where that we can view and we can have a door to place the workpiece. Okay, right. The vacuum environment is vital for preserving the integrity and accuracy of the electron beam machining process. Okay, so here vacuum environment is also playing an important role. Okay, the vacuum range differs from the providing vacuum number, then definitely it influence on the machining process. That means integrity and accuracy of the electron beam machining process. Okay, right. So here, in order to have integrity and accuracy of the electron beam machining, we have to maintain vacuum with 10 power minus 4 to 10 power minus 5 torque. Okay, right. Next, focusing lens. Okay, the focusing lens is a critical component that concentrates the electron beam onto a precise point, reducing its cross-sectional area to a diameter as small as 0.01 to 0.02 mm. Okay, see here, focusing lens, that is electromagnetic focusing lens. So what does it do? It reduces the cross-sectional area, that is diameter as small as 0.01 to 0.02 mm. Okay, so usually the electron beam would be like this, but the focusing lens reduces its cross-sectional area, that is nothing but the diameter should be as small as possible, that is in the range of 0.01 to 0.02 mm. Okay, right. So here finally there must be a single point on the workpiece material to fuse or to melt. Okay, so that it can be done by focusing lens. Okay, so focusing lens is a critical component that concentrates the electron beam onto a precise point. Okay, so otherwise what will happen? Unnecessary heat affected zone will form and the material removal will be in the coarse manner. Okay, right. Here this will be very precision. Okay, so this precision in focusing ensures accurate and controlled material removal. That's what we have discussed, okay, during the machining process. Okay, so here surgical focusing is the main objective of this electron beam machining. So that's why here the focusing lens purpose is that to focus on a precise point, reducing its cross-sectional area to a diameter as small as to 0.01 mm to 0.02 mm. Okay, right. So this is the purpose of the focusing lens in the electron beam machine. Okay, focusing lens work. Right. Electromagnetic deflector coil. Okay. Electromagnetic deflector coil. The electromagnetic deflector coil serves as a versatile function in electron beam machine. It enables the electron beam to be directed to different spots on the workpiece and provides control over the cutting path. Okay, so here what deflector coil will do? So deflector coil will deflects spot. Okay, see here deflector coil deflects the precise point of the emitted electron beam. Okay, right. It enables the electron beam to be directed to different spots on the workpiece and provides control over the cutting path. This flexibility is essential for achieving intricate and precise machining operations. Okay, so here intricate and precise operations we have to go with electron beam machining, and here the purpose of electromagnetic deflector coil is to deflect the focusing or the emitting electron beam point to different spots of the workpiece material. Okay, right. Now let us see EBM process parameters in detail. Okay, so acceleration voltage. So in this setup, the electrons must have high acceleration. Okay, in order to provide that acceleration, we have to maintain the level of acceleration voltage 50 to 60 kilovolts. Okay, and beam current level 100 to 100 microamperes. Okay, next beam power 0.5 to 50 kilovolts. Okay, 0.5 to 50 kilovolts. Pulse time 4 to 64,000 microseconds. Pulse frequency 0.1 to 16,000 Hz. Vacuum 0.01 to 0.0001 mm mercury. That means 10 power minus 4. Okay, this is also equal to 10 power minus 4 torque. Okay, so we have to maintain these levels for the electron beam machining of various parameters like acceleration voltage, beam current, beam power, pulse time, pulse frequency, vacuum. Okay, so these are the different ranges of electron beam machining parameters. Now let us see, this is parameter, EBM parameter. These are levels. Okay, spot size. Okay, so here electron spot size is 0.013 to 0.025 mm. Okay, so imagine how less size it is, spot size. Next, deflection range 6.4 mm square. So it can deflect to 6.4 mm square. Okay. Next, beam intensity 1.55 into 10 power 5 to 1.55 into 10 power 9 watts per square centimeters. Okay. Depth of cut. The laser can reach up to the depth 6.4 millimeters. Okay. Next, narrowest cut 0.025 mm in 0.025 mm thick metal. Okay. Next, hole range 0.025 mm in 0.02 mm thick metal, 1.0 mm in 5 mm thick metal. Okay, so here two things are there. Hole range 0.025 mm in 0.02 mm thick metal, 1.0 mm in 5 mm thick metal. Okay, right. Here spot size, deflection range, beam intensity, depth of cut, narrowest cut, hole range are given with different levels. Right. Next, hole taper. Okay, that is 1 or 2 degrees typical. Hole angle to surface. Okay, so here hole angle to surface is 20 degrees to 90 degrees. Okay, here this hole angle is 20 degrees to 90 degrees. Okay, right. Usually for general purposes we use 90 degrees. Okay, next, removal rate 40 mm cube per second. Okay, so here volume removal rate is 40 mm cube per second. Penetration rate 0.25 mm per second. Okay, performance rate up to 5000 holes per second. Okay, so here electron beam machine can make 5000 holes per second. Okay, right. Tolerance plus or minus 10% depth of cut. Okay, so here if we want to cut with 2 mm depth of cut, 10% means 0.2 mm. Sorry, 0.02 mm. Okay, can be the tolerance. Okay, 10% means 10 by 100 into 2 mm. Okay, so 0.2 mm can increase or decrease, plus or minus. Okay, surface roughness 1 micrometer RA. RA means surface roughness. So these are the EBM process parameters. Okay, so these are the EBM process parameters which are very much important to operate the electron beam machining in the vacuum chamber. We have to maintain all these levels for these parameters effectively. Okay, right. Now let us discuss the advantages of electron beam machining. The various advantages of electron beam machining are high precision with fine detail capabilities. Okay, so here the precision is very high with fine detail capabilities. That means we can make holes with high precision. That means the tolerance will be in the given range, and with fine detail, that means fine detail capabilities means will not affect the other edges or any other features of the workpiece already provided. Okay. Next, minimal heat affected zones. That's what I have said. So here the heat affected zone will be within the range. Okay, preserving material integrity. Okay, so with this electron beam machining, let us say if we machine the workpiece at this point, it should not affect the adjacent zone or any feature of this workpiece material. So electron beam machining is particularly good in affecting or minimizing the heat affected zone of the where we are focusing or removing the workpiece material. So it preserves the material integrity. Right. Next, third one, ideal for heat sensitive and hard to machine materials. Okay, so here the materials may be sometimes hard, we have to work on those, and sometimes the materials may be heat sensitive. Okay, so in general equipment or in general machinery, we can make the features, but at the same time heat effect may be damage the workpiece. So here this electron beam machining is ideal for heat sensitive and hard to machine materials. Okay, so whatever it may be the hardness, the electron beam machining cuts the material. Okay, according to the design and the other parameters involved in that process. Okay, right. Here, no mechanical tool wear, reducing tooling costs. Okay, so here there is no direct contact of any material or tool. So here electron gun emits electrons. Those electrons only fusing the workpiece so that the material removal is taking place. So here there is no question of tool wear. Okay, so that's why we can say that there is no cost about the tool material. Okay, right. Here no mechanical tool wear, so reducing tooling costs. Okay, right. So we need not replace any tools as long as the electron beam functions good, the performance will be good. Okay. Next, minimal distortion in the workpiece. So there will not be any vibrations. Okay. There will not be any heat affected zone and there will not be any thermal stresses involved. So minimal distortion in the workpiece. Okay. So there is no big scope to have some unwanted stresses or hidden stresses for the workpiece material during the working or machining. Okay. Right. Next advantage, capable of machining complex and intricate shapes. So here the electron beam is a smallest point that it can travel according to the set path, so that we can machine with complex and intricate shapes. Okay, so here there is no tool involved. Okay, so suppose if there is any complex shape like this, only a small point can travel over this path, so that we can cut even this kind of complex and intricate shapes. Okay, so here there is no physical tool, only the point. Okay, that is electron beam. Okay, so beam of electrons striking the workpiece material in the set path, so that we can remove the material, whatever it may be the complexity of the workpiece material to be cut and the shape that is intricate. Okay, right. High material removal rates for deep cuts. Okay, so whenever we want deeper cuts, okay, like this, high material removal rates will be possible. Okay, right. No need for coolants or lubricants while machining. So here there is no direct physical tool, and there will not be any question of friction and heat generation. Okay, so no need for coolants or lubricants. Okay, right. Suitable for vacuum and high temperature environments. Okay, suitable for vacuum and high temperature environments. So here we need to create vacuum, because to prevent the collision between the emitted electrons, okay, in the air. Okay, here we are completely removing the air environment. We are creating the vacuum. Okay, so that we are eliminating and preventing the collision of these electrons. Here we need to make the electron beam to a desired direction. Okay, right. Next, last one. Minimal environmental impact due to the absence of coolants and lubricants. So here we are not using any kind of lubricants and coolants. Okay, so that we can minimal the environmental impact. Okay, so there will not be any chemical reaction between the workpiece and the lubricants or coolants. Okay, so that we can minimal the environmental impact while machining. Simply the beam of electron cuts the material, and there will not be heat affected zone, and there will not be any requirement of coolants and lubricants, so that there will not be any chemical reactions between the coolants and lubricants with the workpiece material during the machining of the workpiece. Of course, there are some disadvantages too with the electron beam machining. Some of the main limitations of the electron beam machining are limited to conducting materials. Okay, so here we cannot use all kinds of materials. We cannot use plastics. Okay, this is limited to conducting materials. Okay, next, high initial equipment and maintenance costs. Okay, so usually for mass production or particularly for specialized products only, we have to go with electron beam machining, otherwise it will be cost effective. Okay, why? Because its initial cost is high. Okay, and maintenance cost is also high. Okay, high initial equipment and maintenance cost. Okay, That is one of the drawbacks here. Okay, until otherwise there will be a huge mass requirement, and if it is not that much urgent, or if we don't need that much accuracy, we better avoid direct on bit machine. For simple and general operations involved in automobiles or automobile parts, we better avoid electron beam machine. Okay? Suppose if it is a specialized um, design for the automobiles, we have to go with electron beam machining. Otherwise, we better not to go with electron beam machining. Okay, particularly for medical and other engineering, specialized engineering applications, we have to go with electron beam machine. Next, requires a vacuum environment, limiting workpiece size. Already we have seen that the entire setup should be in the casing, so that we cannot extend the workpiece size. Obviously, the workpiece size must be with less size. Okay, it should be accommodate in that casing. Otherwise, we cannot work on that workpiece. Okay, why? Because we have to maintain the vacuum environment. See here, see, whatever it may be the table size provided in this EBM equipment, that is the only the maximum size can be allowed for the machining process. Okay, right. Next, limited surface finish quality without additional processes. Okay, so here limited surface finish quality. Okay, if we don't have additional processes, then we don't get the ultimate surface finish quality. Okay, that is also one of the drawbacks. Next, limited availability and expertise in electron beam machining. Okay, so here in order to operate the electron beam machining, the skilled labor is required. Okay, and some expertise to operate electron beam machining is also required. Okay, so that is also one of the drawbacks here. Limited availability and expertise in electron beam machining. Okay, most of the manufacturing engineers or operators will deal all other machines. Okay, why? Because electron beam machine is an expensive one, and most of the industries may not be go with electron beam machine. So that's why we cannot find the availability and expertise with electron beam machine. Okay, that is also one of the drawbacks. So we have to try wherever it is required. Next, potential for radiation hazards in poorly shielded systems. Already we have shown that the entire setup is housing with vacuum chamber. Okay, so here potential for radiation hazards in poorly shielded systems. The shielding is poor, then there will be radiation hazard. Okay, next, slower material removal compared to some processes. Okay, though the material removal in terms of depth of cut is good, but in some other operations that may be good, this may be good. Okay, next, complex setup and operation. Though it is travel in the set path with the intricate shapes, the setup may be very difficult. Okay, complex setup and operation. Okay, next, high energy consumption. Okay, in order to emit all these electrons, the power supply will be very high. So the high energy consumption is one of the drawbacks. Okay, right. Now let us finish with the applications. Okay, drilling, perforation of thin sheets, slotting, integrated circuit applications. Okay, so with this, let us conclude. These are the references associated to this topic, and thank you very much. Okay, thank you.
Like, share, and subscribe. Hit the bell icon for more updates.